Okay, welcome back, everybody. I'm just going to sneak in 5 minutes today, and these 5 minutes will deal with how you can add Jupyter to the solution. So for part one, we are basically just doing things which we have seen before. But then in part two, what I normally recommend is actually to add one planet at a time. And we are going to play around with adding Jupyter. And when that functions well, it's pretty straightforward to actually add one more planet at a time. So the thing I would recommend typically when you build the solar system, if you're not too familiar with doing things in an object-oriented way, the easiest way is actually just add one planet at a time. And that gives you also the possibility to spot errors, because you're going to deal with different masses for the planets, and you will see how you can do that in the Earth, Jupiter, Sun case. And when you've seen that, then you basically have the recipe for adding all the other planets. So remember now that we are dealing with a closed system. This is a system with internal forces only, which again means that there will be a force from all the other planets and the Sun to Earth. There will be an equivalent force on Jupiter from all the other planets and the Sun. So we simply have to build up a system where every planet feels a force which is acted upon it from either the Sun or all the other planets. So you will see the pattern immediately when you start adding Jupyter. So let's just bring in that technicality. And as I said in part one, if you just wish to run in 2 dimensions, there's no problem. If you wish to do the 3-dimensional case, feel free to do that. When you come to part two, it can perhaps be convenient to run everything is in 3 dimensions, because the data from NASA on the initial positions and initial velocities, they come in the Cartesian system with the Sun as the mass center. So let's quickly do that, and then we spend the rest of the day on working on the midterm. We will do the same next Friday and parts of next Wednesday. And Shu Yu is going to cater those people which are online. But if you also wish to join online and talk to Shu Yu while she is there, feel free to do that. But let me quickly now bring up the Jupyter case. And then you should have many of the basic details which are needed. So let's quickly do that and change to the whiteboard. And as usual, everything which we do here will be posted, so you can always revisit things. And I will just need some few minutes here so that we should be done rather quickly. Okay, so what we did last week, on Wednesday, was actually to simplify the equations for the Earth-Sun case. So let's quickly remind ourselves about what we did on Wednesday. So we have the Earth-Sun case. And what we did was to use a trick where we rewrote the gravitational constant times the mass of the Sun in terms of 4 pi squared. So this is just us getting rid of a constant. And then this was given in terms of astronomical units. And one astronomical unit is 1.5 times 10 to the 11th meters. So this is to the power of 3. And then we had years to the power of 2. So this is our new kind of units which we have introduced. And that simplifies the calculations because we don't need to carry with us all these different coefficients. So that means for the Earth-Sun case, what we ended up with then is that the acceleration in the x direction, which is the same as dvx dt. So let's quickly remind ourselves about this. This is given by minus 4 times pi squared multiplied with x divided by x squared if we are in 2 dimensions. If we move to 3 dimensions, you would have to add the z coordinate. And that gives you c squared. And similarly, we had the differential equation in the y direction. which now reads simply -4 times pi squared times y divided by x squared plus y squared. And similarly, we had a differential equation for dx dt, which is v of x. And finally, the last equation, if we are in 2 dimensions, then we have 4 coupled differential equations. If we move to 3 dimensions, we will have 6 coupled differential equations. And when we now add a new planet, we can. So what you can decide is to take and bring in all the physical masses, or you can scale them with 4 pi squared. And that makes it much easier when you now are discretizing time, because instead of discretizing times in seconds, you can now discretize times in years. And if you want to simulate for, let's say, thousands or 100,000 years, clearly you don't want to have seconds as your time step, because then your program is just going to run and run and run and never reach the endpoint or the final time. So let's look at the case with Jupiter. So this is part 2. And if you get this right, to include the other planets is just you bringing in the right masses. So now we include Jupiter. And actually, I have to confess that I'm so used to writing Jupiter notebooks that I actually misspell Jupiter, the planet, because it comes with an I instead of a Y. So, but I actually ended up writing it wrongly. So Jupiter, when we do that, we have a mass, which is a factor of 2,000 smaller than the sun. And we're going to play around with different masses for Jupiter. Now, when we now look at the equations, what we need is a force between Earth and Jupiter. But obviously, the Earth sees also a force from the sun, and Jupiter sees also a force acting from the sun. So we need force between Earth and Jupiter. So we need to add that one. And let's just call this for F of E of J, and this is in the X direction. So what we're going to have then is minus G times MJ, and then we have ME, and then we have an XEJ, and this is divided by this REJ cubed. And I just have to give you the definition. So XEJ is simply given by the position of the Earth, so E for Earth, minus the position of Jupiter. In addition, because we have chosen the sun as the center of mass, so all these distances which you see now, they're relative to the sun. So the sun is at rest. And this REJ is nothing but the same quantity which we had for the Earth's sun, but now we need to include these in the calculations. So we have a YE minus YJ, and this is squared. And if you add the third Cartesian coordinate, Z, you have an additional Z term here. Then what we have is a similar term for the force in the Y direction. So that's going to be given by minus G of the mass of Jupiter, mass of the Earth, divided by this distance, REJ, of YEJ, where YEJ is defined in the same way as XEJ. Sorry, Y of J. Now, this force is the same which acts on Jupiter from the Earth, except that the sign changes. So this is again you implementing Newton's third law. So Jupiter feels a similar force, but you have to change the sign. Does that sound okay? So what we would like to do now is to bring in this nice constant, which we had, this 4 pi squared. So if we now look at the expressions, if we take the total force in the x direction on the Earth. So let's define that as force on Earth from the Sun and Jupiter. Sun and Jupiter. If we do that, we can also now take and divide by the mass of the Earth. So that's obviously the acceleration of the Earth in the x direction. And this is going to contain now this minus g of m of the Sun. And this is the position of the Earth with respect to the Sun. This is the same as our magical 1 astronomical unit, this r. And then we have minus g times mj divided by re of j cubed. And then we have x Earth minus the position of Jupiter. Now, what we know is that we rewrote this g times the mass of the Sun. So we can rewrite this as a 4 pi squared times xe divided by r cubed. And then what we do next is that we take this expression and multiply with the mass of the Sun and divide with the mass of the Sun. So what we get then is again a 4 pi squared, but now we have the mass of Jupiter divided with the mass of the Sun. And this is multiplied with xe minus xj divided with the distance between the Earth and Jupiter. So if you look at the equations which you have to program, the only complication now which you have when you add Jupiter is this additional term, but you need to add the same term to Jupiter, but with the opposite sign. And that's due to Newton's law, right? Newton's third law that says that the force acting on one object is equal to the force acting on the other object, but with the opposite sign. And you can simplify things. So what you need to set up are simply the masses. And you find these factors between Jupiter and the Sun. You will have a similar one between Mars and the Sun. You will have the similar one between Neptune and the Sun and all the planets. So that's why it's beneficial when you write the code to do one planet at a time. Because sometimes when you copy and paste, it's actually easy to make an error like that with putting in the wrong mass. And then you will get the wrong results. So the system is actually going to be very sensitive to these masses. So it's extremely fine-tuned. So this is essentially what you need in part 2 to get started. And if you now go into this website of NASA, which we pointed to last time, you can then find all these different masses, the initial velocities and the initial positions. And you can just plug these in and then start simulating the solar system. Any questions about the practicalities? Does it sound okay? So it's more a matter of bookkeeping. And the bookkeeping is something that the reason why I ask you to just do one planet at a time, because I know myself, I'm very impatient. I want to solve the whole thing immediately. And I don't like to wait and do all these small gritty, nitty steps. They're always boring because we as physicists, we want to get to the answer immediately. But in this case, this is something which is worth paying attention to. One planet at a time. Okay, so I'm going to stop here. And just to remind you, if you haven't started with part 1 yet, you find codes in the lecture slides for this week, which give you a good start for the first part of the homework, of the midterm. And feel free to collaborate, again, discuss with each other. Shu Yu is here. I'm going to stop the recording now, and then I will just float around in the room here. And for those of you online, Shu Yu will take care of you guys. I'm just going to stop the recording here.